The next topic that we were talking about as part of this lecture series was about ice and glacial environments, those areas that are predominantly shaped by the work of ice. And so here, in the first place, we're talking about historical kind of events and how the planet has been shaped by ice in the past. So how many like major glaciations there were present on our planet, we should have a kind of a knowledge about these. So we should know when most of these happened. I wanted just here to highlight the difference between LIA and versus the less glacial maximum. So LIA is Little Ice Age. It happened a couple of 100 years ago. And LGM is the last glacial maximum, which was again just a couple of thousands of years ago. So just to make a very quick like distinction between the two, but here instead of speaking about history, I just want to have a look at the theory. And Milankovic, we said Milutin Milankovic was a Serbian geophysicist, and he was working on the theory of why we had climate changes and glaciations in the past. And so here we have Milankovitch cyclicity, which has three main like components, and we just again to have an idea what these are and what we can simply draw, want to say that there was one component which is about really the orbit, the shape and the size of the orbit of the planet Earth around the sun. So this is eccentricity. Make it larger. So eccentricity is about the orbit. Eccentricity is about the orbit. So the path of the planet around the sun. Also, there will be a component here which is about really the tilt. So how the axis of the planet relates to this orbit. And here we said that currently it's around 23.5 degrees, but this has been changing in time. So depending on whether this is a higher or a lower volume, this can be different. And so this is what eccentricity, the official name is obliquity. And this concerns then the tilt. So different words that we can use about the same process. Obliquity is about the tilt, eccentricity is about the orbit, and finally we had a third component which is really about how this kind of axis can be changing, so it's not pointing in the same direction exactly, and that we can draw in such a way, make it nice, somehow like this, that there is a kind of curvy movement, the directional kind of movement here, and that way and that is precession or that is about wobble. So these words we should know, precession and wobble, how this kind of axis of the Earth's rotation axis is not pointing in exactly the same direction. It's kind of like a ball, how you would be able to move. And that's what we did in the past in our classes in Nanjing. I took a ball and we were able then to pretend that it's going to be the planet Earth, and it can not only rotate but actually have this kind of wobbly movement. So it's kind of a relationship between obliquity and to some extent eccentricity. So this is then precession. We should know these. Also, what we were talking about then is ice mass hydrology. I know that lecture about ice mass hydrology, you didn't really understand what I'm talking about, the reasons of the how the water is generated, and I don't want to go through that one again. I'm just saying that ice mass hydrology in the exam will only perhaps a very little bit appear in the sense that we can speak about where we have water as well as ice in this environment. So inglacial, supraglacial, and subglacial we should know about, and to some extent to know that there's albedo, so the reflection of the sunshine. Also there can be some of these reasons of melting from underground, and this would involve both kind of the geothermal heat, but also we need to think about how melting happens because of the pressure. So there's this kind of pressure melting point. This is all we should know about the lecture about ice mass like hydrology. So instead, what we want to think about is how deformation of the ice happens, because that will be relevant for glaciologists nowadays, very important, because deformation will tell a lot about how the ice is behaving, how it is able to melt, or how at all we can speak about ice masses. So that's a very hot topic nowadays for glaciologists. And for this reason, we want to speak about the deformation and the integrated deformation profile, which you already really well know about. So movement, sliding, also kind of a dilation. So this again is integrated deformation profile. We should already remember how these different components would lead to the movement of the surface of the ice as we add up these basal sliding, the deformation of the ice mass itself, and the sliding above this soft material, so dilation of the unfrozen sediment bed. What also we were talking about is just a little bit how the ice is going to act like a non-Newtonian and fluid. So what is this about? Again, it is really about looking at how, compared to water or other materials which would have a kind of really, in this sense, we can say viscosity that is the same. So then we were drawing these kind of charts, or in the PPT you find these. where we said that the stress and the strain will be in some kind of relationship. So the strain rate and the stress rate for water will be something like this. Independently from the amount of stress, the strain rate will be the same. So this means that it has an equal kind of viscosity. So the viscosity, this line really is a straight line, which means that it's the same volume for water. Even though there are no perfect liquid materials, if we're just thinking about the kind of theory of physics. Instead, what we said that there are certain materials which are non-Newtonian, and these can be things like blood or paint or ice, if we see here that the stress level is going to grow, then the strain rate is also going to speed up. What we really are talking about here is that the more pressure we have, the material will much more act like a liquid, a fluid material. And so these we call, if we just want to know about the physics or the kind of theory, the pseudo plastic materials. We don't need to remember it. If you are interested in this, then you can look up this kind of phenomena. And also there are some of these non-Newtonian fluids which are going to be working the opposite way. So if the stress rate is growing, the more pressure we put on the material, then the strain rate is going to kind of decrease. It acts more like a solid, and in this case we can speak about, for example, oblique. So material that is a mixture of the cornstarch and water, and this is where we can speak about the non-Newtonian fluids, which are dilatational. So the opposite kind of process we find with cornstarch compared to ice. And this one I just wanted to show you, so I did this kind of little experiment to show you, because cornstarch is so often referred to, like on the internet, it's a non-Newtonian fluid, but we don't really want to mix it up with the pseudoplastic materials like ice accidentally. So just to show how that behaves, then I added this little video about how cornstarch would behave as a non-Newtonian fluid, and we can think about how ice is related to this kind of movement, this kind of behavior then, that is also a non-Newtonian fluid.